I hope that this is a short video and we are talking about, on this video, we will talk about dispersion, scattering, and polarization. So when a light dispersion, when lights are reflected, the change in the direction is known as the refraction. Okay, when the it's the speed, and we saw this into refraction. Okay, so now when we have two mediums, medium 1 and medium 2, and the light is traveling from medium 1 and is refracted into medium 2, then we can say that the index of refraction of medium 2 is greater than the index of refraction of medium 1, while the light or the wave is traveling on medium 2 with a smaller speed than it is traveling on medium 1, and then the wavelength on medium 2 is less than wavelength on medium 1. And in all those cases, the frequency is constant. We saw this uh, into refraction, the Snell's law. However, the index of refraction depends to a small degree on the wavelength of the light. So, and even though that we say that is the ratio between this and that, the speed of light traveling in the medium and the speed of light in the vacuum, it is to a small degree, it is affected by the wavelength of the light. This effect is so small that it's not noticeable when you have the, the different colors. But when you have a triangular prism, which is known as the Newton's prism, then a white light is broken down into different colors. And it starts from red and then goes to orange, yellow, green, blue, and violet. And this phenomena is called dispersion of light. I will bring a picture and then talk about it. So what do you see when white light is refracted into a prism, which is known as Newton's prism, as I said? Then it is dispersed into the rainbow. So it is going from red, orange, yellow, green, blue, and violet. If you, though, to relate it with the previous video, if you are incidenting a white light into diffraction grating, then the order goes from violet, blue, green, yellow to red. So it's the opposite. When this is pretty much the scattering. Okay. So in terms of the colors, there is this that is known as the subtraction theory of colors, which actually is outside the curriculum. However, it kind of helps to more than subtraction theory of color, the addition theory of color is saying it helps, especially in polarization. So it is saying that blue and red will give you magenta, blue, red, and green will give you white, blue and green will give you cyan, red and green will give you yellow, and everything else added together. So if all the colors are added together, then it is the white light, the light that we see coming from the sun. While the subtraction theory of color attempts to explain the way that objects appears. So when a white light is incident on an object, the object will absorb certain colors and will reflect the remaining. So if you have, let's say, a clear filter, then and you are throwing red, green, and blue, everything will go through. However, if you have a red filter, will absorb the green and the blue, but will let the red pass away. If you have a green filter, then red and blue will be absorbed while green will be filtered. If you have a yellow, remember what yellow is about? It's about yellow color. It's about green and red. So that means that green and red will be allowed while blue will be absorbed. And if you have a cyan, remember what cyan is a blue and a green. So in that case, blue and green will be allowed and the red will be absorbed. If you have a magenta color is as a result of blue and the red. So then blue and the red will be allowed to be passing through the filter, and the green will be absorbed. And if you have a black filter, will absorb everything. So this is what addition theory is and what the other subtraction theory of color is. When we are moving to the polarization, what the phenomena of polarization is when light travels through space, it vibrates. But when it passes through a polarizing filter, the filter allows the light waves through that are polarized in the one plane, in one direction. So in other words, the only light that passes through a polarization filter is the light that was vibrating on the same plane as the polarized filter. I will bring a picture here so that we can explain it. So see here, the light is the source is here, and it is moving, it is vibrating in every single direction. However, we have the polarized filter here that has the axis horizontal. So everything that is not horizontal is prevented, and everything that is in the direction of the polarizing axis, it's allowed to go through. And if right after the horizontal polarizing axis, that is the polarizer 1 here in this picture, you are placing a second polarizer, which is perpendicular. So this is the second polarizer, and if the polarizing axes are perpendicular to the previous one, then nothing is allowed to go through. So what we see here is a net zero intensity. Now, when polarizing filters are parallel to each other, then the light passes through, and when they are perpendicular, then no light is passing through. Now, this is, could those results be explained by longitudinal waves? If the light travel in longitudinal waves, the vibration would vibrate in one direction, okay? Such a wave would pass through a pair of polarizing filter unaffected. In other words, a longitudinal wave cannot be polarized. So based on the polarization evidence, we may conclude that light behave as a transverse wave, not as a longitudinal wave. This is in terms of the polarization, and this concludes the wave nature of the light lesson.